So, yeah, well, thanks for the introduction, and it's a pleasure for me to be here to attend this conference, so I can share you some of our work that is done in recent years regarding the AI-driven design of the fluorescence materials. So, I'm from China, yeah, and yeah, the outline of this talk, including the machine learning paradigm for materials design, and a short background of the TAD of materials, and one of our design case by using machine learning for the TAD of compound design, and also the experimental identification of the design molecules. And finally, I'll give you a prospect in the future. Right. So yeah, well, this is written in Chinese, this page. So basically, a short introduction for the materials genome initiative, which is proposed by the American Energy Department in about 2011. They proposed that by using big data technologies and machine learning for design of the novel materials can dramatically accelerate the design process. So this is compared to the conventional design paradigm, which is appeared in about 1600 by using just the empirical science. So you have to do many experiments and also theories by using trial and error process. So and by the evolution, by the development of the current computational technologies such as the GPU or CPU clusters, so we can actually build such as very complicated neural network structures to simulate the materials properties, even though doing the inverse design of the material. So this kind of process can essentially enhance the efficiency of the material design. Yeah. So basically, in order to do the machine learning design of materials, you first of all have to put the materials into the machine learning model. So which means a very important abstraction of the materials by such as to convert the material structure into the a matrix or a digital matrix, so that can be treated by the neural network or other machine learning models. That is almost the most important step in the machine learning design of the material. So basically, we are involved in the design of the fingerprint of the materials or the fingerprint of the molecules. So there's actually a lot of methodologies for design of the descriptor or the fingerprint of the material, such as you can use some of the gross label descriptors, including dielectric constant or band gap or density or bulk modulus. This is can coming from the experimental data or theoretical data, and use this descriptor to simulate or simulate other properties of the materials. Or this is the K design case of the polymer materials. So you can actually use a molecular fragment which is appear in the polymer, and doing some abstraction to convert this molecular fragment to some of the digital sequences. And this is in our design case. So we normally use the sub-angstrom level descriptors, such as this kind of fingerprint using SOAP, AGIN or symmetry functions, or which is abstracted from the sub-angstrom or angstrom level structural features, or you can call it the representation of the atomic level environment. So if you put this kind of descriptors into the models, then you can actually make a more accurate prediction of the DFT data or Hartree-Fock data. Yeah. So yeah, I can pass it. Yeah. So this is a basic trend of the materials design by using artificial intelligence. So we're actually in here. So this is kind of industrial prediction for the future market size of this of this sector. So we're basically in here. So it's actually in the very initial stage. So, but in the future, by using this kind of very advanced computational technology to accelerate the design efficiency, I suppose it's going to make a huge impact to the materials industry. Yeah. So we actually developed a lot of models using machine learning. You can see lots of these, including deep learning and multitask learning, graph learning, adversarial learning. This is, for example, deep neural network, the most conventional neural network, and recurrent neural network, and this kind of multitask learning for simultaneously predict the many properties of the molecules in one time, and also the graph learning, including graph convolutional network or graph attention, and also adversarial learning, including the AAE, again, GM for the adversarial design, so inverse design of the materials. Yeah, well, this sort of modules is in the process of development. Yeah, so our group is using this sort of modules for we can actually uh, uh, um, find many application scenario, including organic photovoltaics. And this is organic display, such as design of the OLED materials. Is currently the most important work in our group, and also the thermoelectrics and also the lithium-ion batteries. You can also use some machine learning potentials to simulate the dynamics of the ions. That is, in the lithium-ion batteries. So I'm showing you this is some of the machine learning prediction result from our models. So this is the DNN, and you can see this is the basic structure of the DNN. Yeah, this is the input of the feature or fingerprint of the molecule, and data is transferred to several deep layers, and then go to the final prediction target. So this is basically a regression problems, and we're using a QM9 database, so including a dipole moment or Homer normal level or molecular gap, and also some of the thermodynamic properties. And yeah, well, you can see, this database is actually downloaded from the public website, and this is true data represents the DFT data. Yeah, well, we have the high throughput calculation for DFT data, and also this is the predicted data, which is coming from the DNN neural network. Yeah, if you some of the some of the probably you have a very good prediction qualities. So which means you probably have a very high ask rate in the test set. Some of the properties such as a dipole moment or like some these thermodynamic properties, you can have depressed ask rate or depressed prediction result, prediction accuracies. Yeah, so this is a recurrent iron that is borrowed from the natural language processing technologies, and we actually input the molecular smiles into the neural network, and then using the GRU, this is gated recurrent unit, this sort of NLP processing module, and then transfer the molecular smile to the digital sequences, and then put it into DNN, and then get the final prediction output. And this is a prediction of the excited state of the TADF molecules, including the excitation energies and the oscillator strengths and delta ESD, etc. Yeah, some of you can also see some of the probabilities has higher prediction accuracy, some of the probabilities has lower. Yeah, and yeah, I'll pass it. This is for multitask predictions, and this is sort of a graph, a convolutional network by using some advanced abstraction abstraction methodology to aggregate the local environment or local information of the atomic environment into the central atoms, and then get some pooling, get some pooling techniques to convert this a graphical feature, graphical structure or graphical feature into digital sequences, and then put it into the graph MLP, and then gets the final output. So this sort of GCN have much higher prediction, accuracies when it is applied to the same database, which is QM9. And this is adversarial learning by using AAE. I'm going to introduce this later. And this is a GN to produce the image molecules, which is artificial molecules from the computer, and then that can mimic the property of the original samples. I'm going to pass it. Okay, so background of the TADF. So I'm going to very briefly introduce you the concept of these molecules. So we actually have the third generation of emissive molecule by using thermally activated fluorescence, delayed fluorescence. So basically, it has a very high internal quantum efficiency because 75% of the exciton, which is in triplet, can be converted back to the singlet exciton in terms of the reverse intersystem crossing mechanism. So I'm going to pass it. And currently, most of the conventional design by the human experience in TLDF is by using DA structure. You can have this of DA structure, D1D1A or D1A2 or something like that. And then by doing this design, structure design, you can probably have a kind of electron transfer characteristics that can assist the reverse RISC process, to enhance the internal quantum efficiencies. And the challenges of the TADF molecular design is a remarkable fluorescence rate, which is KF, which requires a very strong coupling between the Homer and Numer. It should be well balanced with the minimal delta EST, which actually points to a very small Homer-Numer overlap. So one side is a strong coupling, which is a very strong overlap of the Homer-Numer orbitals. And one thing is to minimize the delta EST, you have to get a very small or a very small Homer-Numer overlap. So this is a contradiction between these two properties. So this is why to look for a good molecule with TIDF properties is very challenging, because only if you use for 10,000 molecule, you may find just several, 5 or 3 molecules that can satisfy the photoluminescence properties. So our design paradigm of the TIDF, including the algorithmic synthesis and the deep predictions and the atmospheric generation fine screening. This is by combining the molecular fragments from the computer programs. We do a combination of the donor and acceptor. By using some of the retrosynthetic procedures. I remember it's Briggs principles to computationally synthesize the original molecules. And then, using SMILES code to put it into the deep predictions for the regression of the excited state properties, and then using AAE to produce artificial molecules, and then doing fine screening from the artificial space, that is produced from the AAE, and then using hierarchical screening to finally screen out the satisfied candidate. Yeah, and this is our database. So we actually built a very large database, and so D1A1 including yeah 160,000, and this is a 5 million molecules for D1A2 structures. Yeah, and we labeled, yeah, we will label the data with high throughput calculations by using TDDFT for calculation of the excited state energy and oscillator strength, and also the delta EST, these sort of things. And yeah, this is a DN paradigm we use for the prediction of the properties. We use extended connectivity fingerprint, yeah, ACFP, which is a very conventional fingerprint to extract the molecular structure features. And then this is the basic prediction accuracies for the excited properties. So for some of the properties like energies, you can see very high accuracies for some of these oscillator strengths, especially in higher order oscillator strengths, you can see very low accuracies. Yeah, so this is graphic representations. And yeah, well, this is a adversarial generation of TADF by using this is well, this is I'm going to pass it because it's a bit complicated. So we generate uh, multiple times. We generate the D1A1 structures for multiple times. And if you generate 200,000, you can actually get or overall efficiency in about 31%. So which means if you get 100 molecule, or if you get 100 molecule in total, you actually have only 31 molecules and eventually to be efficient, or which means yeah, to be different from the original sample, and uh, to be a valid structure in terms of the chemistry, and also to be unique in the database. Yeah, and this is a yeah, well, this is the distribution of the properties for the original space and generated space, which means you will see there's a red line is generated data, the distribution, property distribution of the generated data compared to the original data, they are exactly the same. So which means using this program or using this machine learning models, we generate completely similar, we generate the molecule with completely similar properties compared with the original data set. And look at this is synthetic accessibility and distribution. And in two, the peak value located in about 2, which means it's quite easy to be synthesized. And both of the synthesizability of the original molecule and the generated molecule are quite the same. And it is found it is close to the assay, the synthetic score of the catalog molecule, which means just generating the molecule, we can do theoretically you can do easy experimental synthesis to verify these molecular structures. Yeah, so yeah, well, this is hierarchical screening for the generation space. So we get finally 90 molecules satisfying the photophysical properties, yeah, from the generation space. By almost all of these molecules have band gap or B3 error IP gap smaller than 0.25 electron volt, and all of yeah, which is conditions to be a good candidate of the TADF. Yeah. Okay, so so this is the electronic structure of the generated of the screened out molecules, we can find even though you create this molecule from the computer, they also so this is the experimental aspects for synthesis and characterization of the design molecules. So so this is we choose two molecules from the screen dot database from the 19 potential TADF candidates and do by doing the manual synthesis of these two molecules to verify the structure of the design. Yeah, as the way we choose molecule 12 and molecule 16. And then yeah, but this is a synthetic procedure using palladium catalyzed cross-coupling reactions. And by using NMR experimentation, we can actually identify the structure of the synthesized molecule, and we find, for both of these molecules, NMR indicated structure fully match the theoretically designed configurations for both molecule 12 and molecule 16. And this is a fluorescence spectra of these molecules. Yeah, we'll to verify the photophysical properties of this design molecules. We're doing this sort of experiment, and this is a double check the transition energies and spectra of this molecule by display. Yeah, by display this is the experimental spectra, and the red line is the theoretical spectra that is calculated from ORCA actually using dipole correlation functions to simulate the fluorescence spectra. Yeah, well, you can see the theoretical position of the transition energies completely match the experimental spectrum. Yeah, we'll suggest we will actually design the target molecules with desired photophysical properties. And then this is a PRDK or these two molecules. And yeah, well, there's a slow, a very fast component, a slow component. This is for verification of the delayed fluorescence. Yeah, and also quantum yield. We will find it 9.9% in chloroform for molecule 12 and 9.8% in toluene for molecule 16. Yeah, well, so for a short conclusion, yeah, we design integrated modules combining the several things, algorithm synthesis, the deep prediction, the adversary generation of fine screening to have been built to synthesize and generate molecule with the expected excited state property. And then, the machine learning design molecule have been successfully synthesized and proved to produce desirable photophysical properties, including the delayed fluorescence behaviors and substantial quantum yields, as validating the predictive powers of the ML models. Yeah, well, I think I'm running out of time. Yeah. So finally, I want to acknowledge these collaborators and this institute, which were contribute a lot to our project. Yeah. So thanks for your attention. Yeah.